If you take the high-grade steel used to make a top-tier surgeon's scalpel, right, and you drop it into a vat of warm salt water, eventually it's going to pit.
Oh, yeah. I mean, it will absolutely corrode over time.
Right, it corrodes. But if you take a modern Rolex and drop it into that very same vat, it won't.
It just sits there perfectly fine.
Exactly. And the reason why has absolutely nothing to do with luxury. It has everything to do with a material so incredibly stubborn and, well, difficult to cut that it literally destroys the industrial machines that try to shape it.
Which is such a wild concept, you know? We so rarely look at luxury goods through that lens.
No, we really don't.
The cultural conversation around this brand is just, it's completely dominated by the wait lists, right? The celebrity endorsements, the secondary market. People talk about these objects as if they're basically wearable stock portfolios.
Or just very expensive jewelry.
Exactly, just shiny status symbols.
But the source material we are looking at today completely flips that narrative. I mean, we are diving into a really comprehensive analysis from a material science expert, and their perspective is genuinely eye-opening.
It really changes how you see the whole industry.
It does, because the goal of this deep dive today is to strip away the glossy marketing, the flashing lights, all of that. We are going to look at the staggering, just relentless material engineering that proves this company operates less like a traditional watchmaker and, honestly, much more like a massive cutting-edge materials science laboratory.
Yeah. The author of our source makes a really compelling case that the true intimidation factor of this brand isn't their marketing budget.
Right.
It is their abnormal obsession with metallurgy. I mean, they run their own massive research and development wings and their own proprietary metal foundries.
Which is not normal for a watch company.
Not at all. They are synthesizing materials at a level that most aerospace companies would honestly envy.
So settle in, because by the time we finish this deep dive, you are going to look at one of these watches not as a shiny asset, but as an absolute marvel of extreme human engineering.
Absolutely.
And to really grasp that, I think we have to start with the very first thing you touch, right? The exterior armor.
Yeah, and to appreciate that armor, we kind of have to establish the baseline of the industry. So for almost all high-end luxury watch cases and bracelets, the gold standard is a metal called 316L stainless steel.
Right, which is already a really good metal.
Oh, 316L is a fantastic, highly capable alloy. It is surgical grade. Like you mentioned with the scalpel, it's exactly what you want your surgical instruments made of because it is tough, highly resistant to corrosion, and generally hypoallergenic.
So surgical grade feels like the ceiling. You know, you reach 316L, you dust off your hands, and you say, well, we have the best steel.
Right, you'd think that's where you stop.
But they don't stop there.
No, they bypass the ceiling entirely. Rolex actually uses a super alloy called 904L stainless steel, which of course they've branded as oyster steel.
Now, I know 904L isn't typically found in consumer products, right?
Yeah.
Like, you usually see it in deeply unforgiving industrial applications.
Oh yeah, highly industrial.
We are talking about, what, the piping in chemical processing plants that handles corrosive acids?
Or specific aerospace components.
Exactly. And the reason it is used in those incredibly harsh environments really comes down to its chemical composition. 904L is absolutely max out on 3 key elements.
Okay, what are they?
Chromium, nickel, and molybdenum.
Right, okay.
And when you push the concentrations of those specific elements to the absolute metallurgical limit, something fascinating happens at the atomic level. The steel actually forms a highly dense, incredibly resilient, passive film right on its surface.
So it's essentially creating its own microscopic force field.
That is a great way to put it, yeah. A chemical force field.
And that film is what blocks out the elements that would normally degrade lesser metals, like human sweat, which is packed with salt, right? Or constant exposure to seawater.
Right, the stuff that eats away at normal steel. Under those conditions, 904L theoretically just cannot rust. And as a byproduct of that extreme chemical density, when it is finally polished, it achieves this brilliant metallic luster that standard 316L simply cannot replicate.
It just looks different. But, you know, that passive film is highly effective, yes. But the density of the material introduces a massive logistical problem.
See, this is the part I was getting hung up on in the source.
Yeah.
Because if 904L is this theoretically perfect, steel impervious to salt water, objectively shinier, completely rust-proof, why doesn't every other brand on the market just order a batch?
It seems obvious, right?
Right, because it's a known alloy. It's not a secret recipe. You can just go buy the raw material from an industrial steel mill.
Exactly. Anyone with the budget can purchase 904L. but almost no one else uses it because processing it is an absolute industrial nightmare.
Just because of how hard it is.
Well, hardness is only part of it. Metallurgists actually describe 904L as highly tenacious.
Tenacious.
But-
That's a fun word for a metal.
Right. It means it is tough, it is sticky, and it is highly prone to something called work hardening.
Okay, what is work hardening?
So when you try to cut or drill into 904L, the sheer mechanical energy of the cutting tool actually causes the metal at the point of contact to harden instantly.
Wait, really? So the harder you try to cut it, the harder the metal fights back?
It fights back aggressively. If you run 904L through standard manufacturing tools, you know, the kind of an ordinary luxury brand uses for standard 316L, the steel will literally shred the machinery.
Wow.
Yeah, it strips drill bits, it ruins cutting heads, it just brings standard production lines to a grinding halt.
So the real barrier to entry isn't the price of the raw metal itself.
No, not at all.
It's the millions of dollars in capital investment required just to survive the manufacturing process.
Exactly.
So Rolex couldn't just upgrade their steel orders, right? They had to invent, design, and build custom machines basically from scratch.
From the ground up, yeah.
They had to rebuild their entire factory floor with proprietary tools that were tough enough to stamp and cut this specific metal down to the millimeter without, destroying themselves in the process.
And that massive capital power is their real scientific advantage. They are one of the few entities on Earth that can afford the machinery required to tame the metal.
Okay, so we've essentially built a bunker. The 904L steel blocks the physical elements, the salt, the sweat, the water.
The armor is secure.
Right. But there's a second enemy out there, and it doesn't care about heavy steel armor. It just passes right through it to attack the delicate internal mechanics of the watch.
Magnetism.
Yes.
It is the invisible threat of the modern world.
Let's step inside the watch for a second so we can understand what's at stake here. The beating heart of a mechanical movement is a component called the hairspring.
Right.
We're talking about a coiled spring, thinner than human hair, that twists back and forth multiple times a second. That predictable, continuous oscillation is what dictates the release of energy and actually keeps the time.
And traditionally, that highly delicate spring is made of a ferrous metal, meaning it contains iron.
Which is a huge problem.
It is a severe vulnerability because you and I live in a world absolutely saturated with magnetic fields.
Oh, everywhere.
The speakers in your laptop, your smartphone, the magnetic clasp on a handbag, security scanners at the airport.
And when a traditional iron-based spring passes through those everyday magnetic fields, the coils become magnetized.
Yeah.
They physically attract each other and stick together. So the spring can't, breathe open and close freely, and the timing of the watch is instantly ruined.
Just completely ruined.
It will run wildly erratically until a technician physically opens it up and manually demagnetizes.
Which is a fundamental flaw for a device that is entirely meant to be reliable. So to eliminate this vulnerability, Rolex actually spent 5 years on a dedicated metallurgical mission.
5 years just for a microscopic spring.
Yeah, and the result was a completely novel component they called the parachrome hairspring.
And to get around that magnetism problem, they had to step out of the realm of traditional steel entirely, right? The source notes the parachrome spring is actually an alloy of niobium and zirconium.
Yeah, those are exotic metals. I mean, really exotic. And by combining them, they created an alloy that is completely paramagnetic.
Okay, let's clarify what paramagnetic means in this context, because paramagnetism involves how electrons respond to magnetic fields.
Right.
With traditional iron, the electron spins align with the magnet, which creates a strong attraction. But with this niobium-zirconium mix, the magnetic fields just pass right through without forcing that alignment.
That is exactly the core mechanism. The alloy simply refuses to hold a magnetic charge.
It is so cool.
It is. I mean, you could hold a powerful rare earth magnet directly against the case of the watch, and that parachrome spring will just continue beating perfectly, completely undisturbed.
But I mean, the logistics of making this spring sound basically impossible. Niobium and zirconium both have absurdly high melting points. We are talking well over 2,000 degrees Celsius.
Oh, it's incredibly hot.
So achieving a perfectly homogeneous mixture of metals that barely even want to melt, and then somehow drawing that ultra-hard alloy into a wire thinner than a human hair without it snapping.
It is a staggering metallurgical challenge. It requires vacuum chambers, electron beam melting, and then drawing the wire through these microscopic diamond dies. But you know, the most fascinating proof of their mastery over this material is actually visible to the naked eye. If you look at a parachrome hairspring, it isn't metallic gray.
Right.
It is a brilliant, shocking blue.
Yeah, I've seen macro photos of it. It looks amazing. You obviously can't paint a hairspring, right? I mean, the weight and unevenness of the paint alone would completely throw off the microtime.
Oh, immediately. It would ruin the watch.
So is that like an anodized coating? Or what makes it blue?
It's actually an oxide film. And it's grown directly out of the metal itself through a highly specific heat treatment.
Wait, grown out of the metal?
Yeah. After the spring is formed into its final coiled shape, it is subjected to precise temperatures in the presence of oxygen. The metal reacts, and that blue layer literally blooms on the atomic surface.
And that blue film serves an actual functional purpose. Right, it's not just a visual flex from the watchmaker.
No, it serves a vital physical function regarding thermodynamics.
Okay.
Usually, a metal spring expands when it gets hot, which makes the watch run slow, and it contracts in the cold, making it run fast. But that specific blue oxide film stabilizes the underlying niobium-zirconium alloy. It completely neutralizes thermal expansion.
So whether you are freezing in an Arctic climate or baking in a desert, the elasticity of that spring remains utterly constant.
Exactly. They've essentially isolated the heartbeat of the watch from the thermal and magnetic chaos of the outside world.
Okay, so we've stopped physical corrosion with the 904L steel, and we've defeated invisible magnetic and thermal forces with parachrome.
Right.
But there's a third enemy that attacks basically every object we own. And it doesn't attack the mechanics, it attacks the aesthetics.
Yes, the look of the watch.
Right. Ultraviolet radiation and chemical oxidation. Because, I mean, how do you engineer a material to pause its own physical aging process?
Well, their philosophy is that a watch should look the exact same decades from now as it did the day it left the factory floor.
Which is a tall order.
Very. And the clearest example of this battle against aging is the bezel. You know, the rotating ring around the watch face, particularly on their sports models.
Right, and historically those are made of aluminum. And if you look at vintage watches, those aluminum bezels are always scratched, and the colors, like the reds and blues, are heavily faded by the sun.
Because aluminum is soft, and its pigments just break down under UV light. It's inevitable. So to solve this, Rolex developed Cerachrome.
Okay, Cerachrome.
Yeah, and this is not the ceramic of a coffee mug. We are talking about advanced industrial ceramics, typically synthesized from zirconium dioxide or alumina.
And the manufacturing process for this is just wild. The source says they take this microscopic ceramic powder, inject it into a mold under immense pressure, and then sinter it.
Right, sintering.
Which essentially baking it at roughly 1500 degrees Celsius.
And during that sintering phase, the ceramic physically shrinks by about 25%.
25%, that's a huge shrinkage.
It is. But what happens is the powder particles fuse together, condensing the crystal lattice into an incredibly dense state.
So the resulting material is so hard that practically only a diamond can scratch it. I mean, you could drag a steel key across it, and the key would just slide off without leaving a mark.
It wouldn't do a thing.
Furthermore, the color is structurally baked right into the ceramic. Ultraviolet rays from the sun simply cannot break down those molecular bonds. The bezel will be the exact same shade of blue or black a century from now.
But the bezel also has functional utility, right? I mean, it requires tiny, precise numbers and graduations marked all over it to actually be useful.
Right, and this is where I get completely hung up. If the ceramic is that impossibly hard and slick, how do you mark it? If you try to paint numbers into the grooves, the paint would just flake right off a surface that's non-porous.
Exactly, so they don't use paint. Those microscopic granulations are actually filled with atomized layers of real gold or flat.
Recommends gold.
Yes. And to achieve this, Rolex uses a technique called physical vapor deposition, or PVD.
Literally vaporizing precious metals.
Literally. They place the entire ceramic bezel into a vacuum chamber filled with argon gas.
Okay.
They bombard a target of pure gold or platinum, knocking atoms loose, which then travel through the vacuum and coat the entire bezel atom by atom, penetrating the recessed numeral.
That is insane.
It is. And afterwards, they polish the flat surface of the ceramic. The gold wipes away from the hyper-smooth top layer, but it remains permanently fused inside the recessed numbers.
It's an absurd level of molecular engineering just to make sure the numbers on a dial don't chip.
Just to avoid chipping.
But speaking of precious metals, the source material brought up their proprietary foundry work, specifically regarding their pink gold. Because pure gold doesn't actually age well on its own when it's mixed to create colors.
Right, and this is one of the clearest examples of Rolex basically acting as an applied chemistry lab. Standard 18-karat pink gold actually has a fatal chemical flaw.
Oh.
Pure gold is yellow, obviously. To achieve that beautiful reddish pink hue, jewelers create an alloy by mixing the gold with silver and, crucially, copper.
Right, the copper provides the red tint,
Yeah.
but copper is highly reactive.
Highly reactive. As standard pink gold is exposed to everyday elements like, oxygen in the air, chlorine in a swimming pool, or sulfur in a hot spring, a chemical reaction occurs.
Yeah?
The copper inside the alloy oxidizes and literally begins to leach out of the molecular structure of the gold.
So over the years, as the copper is stripped away, the beautiful pink hue fades, and the watch slowly turns back into a patchy, dull yellow.
Exactly.
And for a company obsessed with freezing their products in time, an aging, fading metal is just unacceptable.
Well, their in-house foundry set out to solve a chemical degradation problem that has genuinely plagued jewelers for centuries.
Wow.
And the solution was their proprietary alloy, Everose Gold.
Right. So to stop the copper from leaching out, they blended in a very specific percentage of platinum. But, just tossing platinum into the melting pot isn't enough.
Right.
The source mentions they had to perfect the phase transformation of the alloy.
Right. The phase transformation is the critical moment. As liquid metal cools into a solid, the atoms snap into a grid, a crystal lattice.
Okay, I follow.
If the alloy cools unevenly, the copper atoms might clump together, leaving them exposed and easy targets for chlorine to attack. But by ruthlessly controlling the temperature drop, Rolex ensures the platinum atoms are forced evenly between the copper and gold atoms across the entire grid.
Oh, I see. Okay, so think of the gold and copper atoms like the bricks and mortar in a wall.
Okay, yeah.
Over time, the chlorine and sulfur act like harsh rain, washing the mortar, which is the copper, away. But what the platinum does is it acts like structural rebar woven perfectly through those bricks.
That is a great analogy.
Right. It locks the copper into the molecular structure so tightly that the chlorine literally can't pull it loose.
That structural analogy hits the nail on the head. The platinum stabilizes the copper right at the atomic level. And because of this, the pink color of the watch is chemically shielded. It stays pink, quite literally, ever forever.
Everose. Man, when you lay all of these innovations out on the table, it completely reframes the object. It means it is really time for you to look past the wait lists and the celebrity risks. A Rolex is far, far more than just a way to show off a bonus check.
It really is. It is a triumph of universally applied material science.
Yeah.
From the extreme, work-hardening 904L steel cases that require custom-built factory lines just to survive the cutting process,
Right.
to the paramagnetic Pericommerm hairsprings that completely defeat the magnetic and thermal chaos of the modern world.
And to the sintered ceramics and the Everose gold that literally halts its own chemical aging at the atomic level.
They are synthesizing perfection in a laboratory.
So the next time you see one of these watches, I really challenge you to look at it as an awe-inspiring crystal of human metallurgical technology. It is a masterclass in pushing elements to their absolute limits to create something permanent.
It really is the physical manifestation of scientific obsession, worn on the wrist.
But as we bring this deep dive to a close, there's one final, slightly philosophical question that this incredible science leaves us with. And it's something I want you to mull over today.
Ooh, I like this.
We just spent this entire time marveling at how material engineering can effectively stop physical aging, right? We can freeze an object in a state of permanent, scratch-free, unfading perfection.
Which is, of course, the ultimate goal of the manufacturer.
Right. But if an object never ages, if the bezel never fades in the sun from that long road trip you took, or the steel never gathers a micro scratch from the time you accidentally bumped it on your child's crib, if it never develops a unique patina from the like you've lived with it, does an object that is perfectly frozen in time actually lose a tiny piece of its personal history with you? I mean, if the material never changes, does it ever truly become yours? Think of it that the next time you look at something engineered to be perfectly shiny forever.